G'day chemistry students. In this video we're going to be looking at dot points 4.2.1 and 2. In the next two videos we're going to be looking at Hess's Law. This is part 1. Now to start off with, to understand Hess's Law, it's really good to go back and look at the concept of the law of conservation of energy. It's the idea that energy cannot be created or destroyed, it can only be transformed from one form to another. So the general idea here is that chemical energy can be turned into heat, light, electrical energy, and vice versa, and that's achieved through the formation and breaking of bonds. So already we've looked at the concept of an exothermic and an endothermic reaction transforming energy. In this Hess Law concept, we're going to take that idea a little bit further. So the main idea with Hess's Law is that reactions don't always just go from A to B, from reactant to product. A lot of the time, there are what we call intermediate processes. So chemical reactions that help us get from A to B. A lot of the time, those reactions are not direct. In these cases, what we will see is that the enthalpy changes for all of the intermediate processes will essentially all add up to be the same as the enthalpy change that we see from beginning to end. So a lot of the time you might see Hess's Law expressed with diagrams. There are also ways of showing it mathematically, but the main idea here is that we can have a set of reactants here, A forming products B, but A may not just go directly to B and have an energy of delta H for the reaction. What we may see is that there may be one or more steps. Here we have A to X, X to Y, Y to B, where there are essentially three different enthalpies, which would then add up to the enthalpy of the reaction overall as those intermediate steps move forward. Now, in this example down the bottom here, what we see is that delta H for the entire reaction is positive. But that doesn't mean that all of the delta H's for the intermediate processes need to be positive as well. They don't all need to be endothermic. In particular, delta H for process 1 absorbs more energy than the reaction to begin with. And what we see is that sort of balanced and cancelled out by the following reactions, where the delta H for reaction 2 from X to Y is an exothermic process, and delta H for reaction 3 for Y to B balances everything out, and it ensures that we go from 20 to 10 to 15 joules, which is the enthalpy for the entire reaction. And we can see here that really all we're doing is just adding up each of those enthalpies to get to the delta H for reaction. So when we start doing calculations with Hess's Law, a lot of the time we're given information about some of the processes and we're trying to find out what the enthalpy change is for one of the processes. So that could be trying to find the enthalpy change for the entire reaction, meaning that we would be given all of the other parts. Maybe we're given the enthalpy for reaction and we know some of the parts, but one of those parts are missing. And so we can do some quite simple math to be able to determine what that missing energy change is. And in a lot of these cases, what we end up having to do is get given standard data and then manipulate the equations so that they'll actually work for the calculation. Now, at the moment, that won't make a lot of sense until I actually show you what that looks like. But what I want to emphasize is that we may need to change the enthalpy of some of the data that we're given, some of the known values that we're given, because we need to manipulate what the equation looks like. So in this example on the left, what we can see here is that to do the Hess's Law calculation correctly, in this example, we have flipped the reactants and products. And essentially what that means is that this forward process that is exothermic becomes endothermic when we write it out as a reverse process. Now, the size of the energy change is exactly the same, but the polarity is different. Over here, we've got our reactants and products on the same side, but to get the Hess's calculation to work correctly, we need to change up the stoichiometry of the reaction. So that essentially means doubling all of the reactants and products. And if we have double the number of moles of reactants and products, we're expecting double the energy change as a result. So we can see that on the right there as well. Now, when we're going to be doing any of these Hess's calculations, usually what I'll be asking you to do, or what you should be doing, is first identifying all of the equations that have been given to you. So either writing them out again if they've only been described to you, or simply just numbering them usually works. Writing out the equation that we don't know the enthalpy change for, you can then go about manipulating the equations that you've been given and as well their enthalpies, just like I showed in these examples here, so that you end up matching the reactants and products in your given equations to the reactants and products for the equation of unknown enthalpy. Again, that'll make a little bit more sense when I actually show you an example in a moment. Once you have manipulated all of those equations, you can add those equations together and cancel out any molecules that you might find on both sides. And then as well, then add up their enthalpies, and that will end up giving you the unknown enthalpy. But let's go have a look at an example question to sort of show how those steps look and how they work. So in this question, we're being told that carbon combusts in the presence of oxygen gas to form carbon dioxide. However, the reaction has an intermediate product. Carbon first forms carbon monoxide, and we've been given two equations that show this, so that carbon and oxygen reacting to form carbon dioxide, and we've been given its enthalpy. But we also have carbon reacting with oxygen to form the intermediate carbon monoxide, and we've been given its enthalpy there as well. Now, this carbon monoxide will further react with oxygen to form carbon dioxide, and we're being asked to determine the enthalpy for this intermediate step. So what we've got to do first, according to our steps on the side for calculating a Hess problem like this, is first write out or identify all given equations. Now they've already been written out, so I'm just going to identify these two equations as 1 and 2. Now the next thing that we need to do is write out the equation of the unknown enthalpy. So at the moment, we don't know what the enthalpy change is going from carbon monoxide to carbon dioxide. So we know though that carbon monoxide will react with oxygen to form carbon dioxide. And at the moment, delta H is unknown. Now at the moment, this equation isn't balanced. So we're going to be reacting with half a mole of oxygen to ensure that we have the right number of oxygens there to form our carbon dioxide. What I'm also going to do is label this reaction as number 3. If we look at step number 3 over here, we then need to manipulate the given equations and their enthalpies to match the reactants and products of the equation for the unknown delta H. So when we look at our reactions here, we're kind of looking for the unique reactants, ones that we don't see in other equations. So for number 1, that means that we're looking at the carbon dioxide, and for number 2, we're looking at the carbon monoxide. At the moment, equation 1 is exactly the way that we want it to be. We have 1 mole of carbon dioxide being produced here, and 1 mole of carbon dioxide being produced in equation 3. However, for equation 2, we have carbon monoxide, which matches the reactants of reaction 3, and they're in the same ratio. They're in a 1-to-1 ratio, but the carbon monoxide is on the wrong side of the equation. So we're actually going to have to construct equation 4 before we get started. And equation 4 will be the same as 2, just with the reactants and products being flipped. So that will look something like this. Now, the enthalpy for this reaction is going to be the polar opposite of the enthalpy of its reverse, or the enthalpy of equation 2. So because we've just reversed the reactants and the products, we also flip the polarity of the enthalpy. And the last step is to add the manipulated equations and their enthalpies together. Now, that may seem a little bit weird still, but you'll hopefully understand a little bit more when I actually do it. We've set up equation 1 and 4 to match what we're expecting in equation 3, the missing reaction in this Hess problem. So we've got carbon monoxide on the right side for equation 3 and 4, carbon dioxide on the right side of the equation for 1 and 3. What that means is if we add 1 and 4 together, we should end up with equation 3 at the end. So I'm going to physically do that to sort of show you. So what I'm going to do first is write all of the reactants out. So the reactants for equation 1 is carbon plus oxygen gas. We're also adding the reactant for equation 4, which is carbon monoxide, and that is then going to result in all of the products. So the product for equation 1 is carbon dioxide, and the products for equation 4 is carbon and half a mole of oxygen gas as well. From this point, we can then go about cancelling out any molecules or elements that are on both sides. Note as well that there is oxygen on both sides, but not in the same ratio. So this 1 mole of oxygen will just become half a mole of oxygen. And then we're left with our carbon monoxide and our carbon dioxide. So the overall equation looks something like this: half a mole of O2 plus a mole of carbon monoxide, forming a mole of carbon dioxide. And you'll notice that this equation here matches what was described up the top, that the carbon monoxide will further react with oxygen to form carbon dioxide. Now the only question is, what is the enthalpy? Note as well that this matches equation 3 like we wrote before. Now because we formed equation 3 by putting equation 1 and equation 4 together, the same thing has to happen with the enthalpies as well. So to find the enthalpy of reaction 3, we need to add together the enthalpy of reaction 1 and the enthalpy of reaction 4. In other words, that would be negative 394 joules. And we're adding that to the enthalpy of reaction 4, which is 111 kilojoules per mole. Now, this results in 283 kilojoules of energy. And that is the solution to our question using the Hess concept. Thank you very much, everyone. In the next video, we're going to take this Hess concept a little bit further and start to look at other ways that we can be looking at the progression of reactions quantitatively. But until the next one, have a good one.